So we're going to get started. So our afternoon session, hopefully you enjoyed Chan's tutorial on how to create cohort definitions. Got a little bit of exposure to Atlas. And hopefully you enjoyed lunch, or if you, while you were doing your lunch, you enjoyed playing with Atlas a little bit more. So the premise that I shared with you before Chan presented was that if you could create cohorts, then those serve as inputs to all of our standardized analyses. And so Jack, when he presented yesterday, he showed how there was a wide collection of different analysis questions that were asked, and all of those were using standardized analysis modules that used cohorts as inputs. So this session, what I'm going to actually do is walk through with you various standardized analysis modules that we have available and show you what the input parameters are and show you how we made choices for the fluoroquinolone study for each of those modules. What I'll highlight for you here is that we've something that Martin Schumi has been driving in our community is that we're trying to establish not only a way to do standardized analysis, but a way to standardize the way we do standardized analysis. And the specific, the detail there is that what we learned was that we had lots of different ways to do standardized analysis. Every package had its own way of defining inputs. Every package had its own way of defining outputs. And so that even though we had standardized packages, our way of doing characterization was different than our way of doing estimation, which was different than our way of doing prediction. And so within the OHDSI community, under Martin's leadership, what we've now actually done is harmonize the way that we think about all of our analysis packages, such that they all basically now follow the same basic rubric. And that basic rubric is quite simple to describe. Every package has to have an input specification. That's basically the list of parameters that you define how an analysis is going to run. And those input specifications are all written formally as a JSON file. So just like Chan showed you that we have a JSON representation of a cohort definition, we have a JSON representation of each of our analysis modules. And that JSON file serves as an input to each and every one of our standardized analysis modules. So every module, no matter what it's doing, whether it's characterization, estimation, prediction, it's going to take as an input a file in JSON format that contains all of the input parameters to run an analysis. And so really, for most of you who hopefully are primarily just users of these tools, the only thing you need to know is, how do I create that JSON file? How do I specify the input parameters to this package so that it can run? Additionally, every analysis module is now going to produce a standardized output. And specifically, all results will be written into a list of comma-separated text files. And the point of this is that no matter whether you're running a characterization, estimation, or prediction, what you're generating is a series of aggregate summary statistics. You're never sharing patient-level data. You're only generating aggregate statistics. And those statistics are actually going to be formatted in a very specific construct that specifically represents a results data model. So just like we think about the OMOP common data model as a way to represent patient-level data, we've now actually created a data model to represent aggregate summary results or evidence that we produce. And every module outputs results in CSV filed text files that can be inputted into this results schema. Now, each module gets to decide what the schema looks like. So each module determines what the tables are and what the fields are. But every single package, if you run it, you'll always know that if I run it, I have to pass in a JSON file as an input, and I'm going to get a set of CSV files as an output. And those set of CSV files can then be loaded into a relational database, and then we can do lots of fun things like have a Shiny app that sits on top of that result schema that allows you to do interactive exploration of the results. And I think later this afternoon, Jack's going to walk through the Shiny app, so you all will actually get to experience that. The reason I'm starting here is that all of this idea of no matter, even though we're going to show you some very advanced statistics, the basic idea is to make everything the same workflow for everybody, no matter what you're trying to do. And so the value promise of standardizing analytics is twofold. One is from a technical perspective. Let's standardize what an input is. Let's standardize what an output is. Let's make running a package be the consistent experience no matter what we're doing. And hopefully that will reduce the barriers to entry. Will make it a little bit easier for all of you to be able to adopt this and approach it. The second component of standardized analytics is that we are trying to develop and evaluate scientific best practices for how to do each of these components. And so by having this standardized input and standardized output, it means that you all don't really have to worry about what's happening in between the input and the output, but instead you can become familiar with what exactly it's going to do. And within the community, we've made tremendous progress on establishing scientific best practices for how to run a characterization study, how to run a causal inference study, how to do machine learning and patient-level prediction. And each of those is kind of the stuff that's inside of the box. And so what I'm going to walk through over the next 45 minutes or so is I'm going to give you a fast tour through all of the modules that are currently available with specific examples of how we used them for the fluoroquinolone study. What I encourage you to think about is twofold. One is, how may I want to apply these modules to a question that I may have? And what you'll learn is, and if you jump out into Mark's breakout, you could even learn like how you would actually run that yourself for your own question. But also I want you to think about the fact that within the OHDSI community, we already have built quite a lot of modules, but we're nowhere near done. We're barely just getting started in terms of all the capabilities we could bring to the broader community. But if we have the same guiding principle that every module will have a standardized input and a standardized output and will follow this approach, then it means all of you, if you come up with a new type of characterization analysis or a new method for doing causal inference or a new machine learning algorithm, you can follow the exact same design cadence to contribute a new module into this entire pipeline. And what we've now created is something such that now, through this strategist package that Martine's created, quite literally, there's one JSON file that describes all the different modules you're going to run with all their input parameters. There's a single execute function that just says execute, and you pass that file, and it'll run through all the characterizations and all the estimations and all the predictions. And then at the end, you just have a large series of results files that can be all loaded as one big job into a result schema, which means that you can, as we will show you, you can do extraordinarily advanced statistics across a wide range of things with effectively one series of commands in R to be able to run everything together. So I'm going to walk through the specific details of the modules, but I want to give you kind of that big picture perspective of how this all fits together and how these individual trees that you're going to see kind of make up the forest that represents our OHDSI open technology stack. All right, so I highlighted this yesterday, that what we're really thinking about here is we're trying to engineer an open science system to generate reliable evidence. Up top here in this schematic, because we'll use this again, the first premise of this is that we need to standardize our data to the OMOP common data model. So you got that demo from Mui and Song earlier today. The components that we've been talking about is that we want to be able to have diagnostics associated with identifying the databases that are fit for use, identifying how to create and evaluate cohorts. So today, Chan shows you how to create cohorts. We didn't get into the process of how to evaluate them, but there's a wide array of tools there. And only after you've identified the data that are appropriate and you've identified the cohorts that are appropriate do we move into study diagnostics, which is where we actually execute the particular statistical models. And those statistical models that we run produce two types of outputs. One is the answer to the question you asked, and the second is an assessment of whether or not we can trust the answer that we just provided. And this is by having these objective diagnostics that are basically rules that tell us whether or not we can actually believe the evidence that we've generated. And it's only after we pass all of those tests that we would actually unblind those results we've now generated and make them available. So today, what I'm going to be talking about for the analysis design is really in this third box. It's given that we've found databases, given that we've created cohorts, what are the set of analysis modules we would like to run, and what is the way that we specify the inputs to run those. After I go through the design, if you break out into Mark's session later, you'll also be able to see how do you actually execute that design and run that study in your data. And for those of you who stay in this room, you'll be able to see, given that the analysis has been executed, how do I actually explore the results that are the output of these processes. All right, so I'm not going to go through study initiation or the research questions, but I want to encourage you, and I'm going to go through these again because I think it's useful. When we conducted the Sisyphus Challenge just a couple months ago, each and every one of these activities was recorded as a full tutorial that's available on the OHDSI website. So if you're interested in initiating a study, you should check out the tutorials by Mark and Chan. You can learn about the research questions that we did. I'm not going to talk about data diagnostics, but I encourage you to take a look at the tutorial that Claire and Sarah and Mui and Jing provided about data diagnostics. We're not going to talk about phenotype development evaluation. You just got exposure to Atlas as a tool for creating cohorts, but there's quite a lot as it relates to estimating the measurement error associated with a cohort. I encourage you to take a look at that. What we are going to focus on right now is designing the actual specific analysis modules so that we can, so I can expose you to what are all of these open source standardized analytic tools that are available, and what choices do you need to make as a designer of a study inside of each of these modules to run them. And then after this, we're going to go through reviewing the diagnostics and evidence synthesis. And Martine's specifically going to talk about how to interpret the diagnostics and how to conduct a meta-analysis based on the results. So the modules that I'm going to talk about today are the ones that were available at the time that we ran the strategist pipeline for purposes of the SOS challenge. So there are an array of different types of characterization analyses. There's patient-level prediction, and there's population-level effect estimation. So for characterization, there is a tool called cohort diagnostics. This is one of our tools to evaluate phenotypes, whereby you can summarize a given cohort definition and understand whether or not it looks like it's capturing the patients you had intended. We have a module called cohort features, and this allows you to say, given that I've got a cohort, so you all just created two cohorts. You created an exposure cohort of fluoroquinolones. You also created an outcome cohort of aortic aneurysm. Given those two cohorts, you might just want to understand who are the people that belong to those cohorts. What are their demographics, their prior conditions, their comorbidities? And the cohort feature module is going to provide a standardized way to summarize that information. We have an incidence rate module. And that allows us to say, given a target cohort, in our case, we can say the fluoroquinolone new users, how often do we observe aortic aneurysm occurring within some time horizon? And Jack talked about yesterday that we focused in the presentation about like a 60-day window. So you could specifically ask the question in the incidence rate package, amongst new users of fluoroquinolone, how often do we observe aortic aneurysm in a 60-day window? And this will provide you a proper epidemiologic incidence rate for any target and any outcome that you desire. We have a time to event module analysis. So given that I've got a cohort of people that have fluoroquinolone use, and I have a separate cohort of all of these aortic aneurysms, one question one could ask is, when do aortic aneurysms happen relative to fluoroquinolone exposure? See, in the incidence rate, and as Jack presented, we had to actually specify a time at risk of 60 days. But one might just want to have the data help us understand how often, or when do events happen in relation to exposure. And this can also be quite helpful because we can also look not just after entry into the target cohort, but actually prior to entry into the cohort. It could be, for example, that we're not really looking at a causal effect of fluoroquinolones and aortic aneurysms, but rather maybe these things just for whatever reason actively co-occur. And maybe there's a bunch of aortic aneurysms right before they got an antibiotic exposure. And this is a module that actually provides a descriptive summary to let you see that. And then the last characterization module that was available at this time was a D-challenge, re-challenge module. So to show of hands, how many folks have worked in the pharmacovigilance space at all? A couple hands, not very many. So when studying drug safety events, and particularly with dealing with spontaneous adverse events, adverse event reports, whereby a clinician or a provider says, I suspect that I had an adverse event caused by a drug, there's a series of questions that get answered on forms that are submitted to the FDA or EMA or TGA or wherever it might be. And one of those questions is about the individual case's experience, individual person's experience as it relates to the idea of D-challenge and re-challenge. D-challenge is the idea of, I took a drug, I had some bad thing happen to me, so I D-challenged by stopping the drug. Did the event go away? So, I took a drug, I got a rash, stopped the drug, the rash went away. That would be a successful D-challenge. And the argument in the pharmacovigilance world is that's some additional information, like an N of 1 experiment, that maybe that adverse event was truly caused by the drug because removal of the exposure removed the event from happening. A re-challenge is, I took the drug, I had a rash, I stopped the drug, the rash went away, I waited a little bit of time and I said, you know what, I'll try that drug again. I try the drug again as a re-challenge, and then the rash comes back again. And in the pharmacovigilance space, when we see these re-challenge cases, many in the drug safety space consider this to be pretty compelling evidence of an N of 1 experiment, whereby some person had an exposure, had an event, removed the exposure, the event went away, had the exposure again, the event happened again. That could be a compelling narrative about a causality. Now, this is what gets answered on these spontaneous adverse event reports. What we've done in the OHDSI community is actually create an observational data analog to that by looking for that experience within a given patient's record. So we will actually use the longitudinal data within a patient's chart in the CDM to basically look to count up how many times do we see one of this D-challenge attempts, how many times do we see the re-challenge attempts, and that information can complement the other characterization analyses. Patient-level prediction. Again, the idea here, the question as it relates to fluoroquinolones would be, if I knew which patients were initiating treatment for fluoroquinolones, I could ask the question, which of those patients is at highest risk of going on to have an aortic aneurysm? And then lastly, when we talk about population-level estimation, there's a wide array of different epidemiologic study designs that can be used to try to elicit a causal effect. And here what we're really talking about is estimating a relative risk or a hazard ratio or whatever estimation metric that you'd like. The two modules that we executed here was a comparative cohort design, the idea that you take a cohort that's your target population, compare them to a cohort that's your comparator population. We're going to do some adjustment, and Jack walked through the use of propensity scores as a modeling approach to try to make those groups similar. And then we look for the relationship to the outcome. But there are a wide array of other types of epidemiologic designs that can be used for causal inference. The other one that we ran, but we didn't touch on very much yesterday, is a self-controlled case series design. The idea that a given individual serves as their own control, whereby the period of time they're exposed is contrasted to the period of time that that same person is not exposed, and you look at the differential rate of events. Within the OHDSI community, we also have other estimation modules. We just didn't run them here, so I'm going to talk about these too. The important thing for all of these modules, though, is even though these are very, very different things, characterizing D-challenge, re-challenge versus estimating a causal effect, all of these modules work the exact same way. They have a standardized input, JSON file. They have a standardized execution. We're using the strategist framework, so there's basically an execute function in R to run these things, and they have a standardized output. So that's a CSV file that can be loaded into a results schema. And because all of these modules run the exact same way, what it means is we can just compile all the inputs into one big JSON file, and we can get to see all the results come out at the end, no matter whether we're asking one question of one drug or we're asking questions of dozens of drugs and dozens of outcomes. Whether you want to do a lot of estimation or just prediction or just characterization, all of that's possible within this one unifying framework that we're using. Okay, so design decision choices that always need to be made as input to standardized analytics. So the reason we went through cohort definitions first is because almost always, I'd probably assert always, you are going to need to define some target population of interest. And very often, if we're going to be talking about causal effects of some sort of medical intervention, the target cohort is the intervention itself. So it's what exposure are you asking your question about? In our context, that's our fluoroquinolone exposure. It's quite often the case that we are going to want to specifically nest our target cohort within some indication. And so you heard Jack talk about in the case of the fluoroquinolone study that we decided to specifically look at fluoroquinolone exposure amongst patients with urinary tract infection. And indeed, fluoroquinolones have multiple different indications, and we could have studied any or all of those different indications, but you actually need to specify that list of indications that you're intending to treat. All studies should have some list of outcomes, so you can think of those as specifically the events that we're looking at. It's possible that you want to define a comparator group. Certainly, if we are going to use a comparative cohort design, a comparator is going to be required. The primary thing that we want you to think about here is you're trying to define some population that's serving as the proxy for the counterfactual. That is to say, you kind of want the people that would have been eligible for the target cohort, except they didn't actually get the drug of interest. And so in the case of what Jack presented, we talked about using other types of antibiotics, such as cephalosporins, as a comparator, not because we had any belief that cephalosporins have anything to do with aortic aneurysms, but rather we're trying to find people that are kind of like those fluoroquinolone users in all different baseline characteristics, except that one group got fluoroquinolones and one didn't, and that cephalosporin serves as that proxy. Most analyses require that you, the user, define the time at risk. So this is the span of time relative to the exposure when the effect of the outcome is hypothesized to occur. And so in our fluoroquinolone study, we actually defined a range of time at risk windows, or a set of time at risk windows, because it's actually not clear what that clinical hypothesis is. So Jack summarized and highlighted what we saw for the 60-day window, but in fact, as he mentioned very briefly, there was 4 different time at risk windows that were explored in the study. There could be reasons why in a given analysis you are going to restrict to age, sex, or calendar time. We advocate the idea that negative control experiments are an essential part of any given design, particularly if you are doing causal inference. And so we assert that you should define these negative controls up front. If you are going to be trying to fit some sort of predictive model like a propensity score, you need to be able to define what things you don't want to include in your prediction model. The reason why I go through this list is basically the way that we've now structured all of our strategist work is if you can make these design choices, which you may notice correspond to those fill-in-the-blank templates that I showed you before, if you can answer these questions, you can now specify the fanciest, most advanced OHDSI study that you could imagine simply by plugging in, filling in these blanks, and then running strategists across all of our modules. The other thing I want to highlight is that almost all of these, I think all of them say in parentheses S. One of the things that I'm quite proud of that we've done in the OHDSI community, and I give big credit to Mark and Martine for leading this, is we've always been thinking about developing tools to handle the case of doing large-scale analytics. We believe that we need to get away as a research community from everybody just cobbling together a one-off question where they have one question on one database using one analysis to produce one answer and then not knowing whether or not it can be trusted. And part of the way that we get there is develop standardized analytics that don't just do one-off studies, but rather if there is a best practice way to do estimation and a best practice way to do characterization and a best practice way to do prediction, then it should be the case that I don't have to pass in one question at a time to this machine, but rather I could pass in a list of targets and a list of comparators and a list of outcomes, and the same analysis procedure will be consistently and reproducibly applied to every one of those combinations of questions that you're asking so that you remove the threat of investigator bias and p-hacking that plagues our field. And so within this strategist framework, quite literally, you can just pass in whatever set of combinations of questions you want and have confidence that you're going to get the same type of analysis back no matter which question you pick and choose to look at. All right, so I'm doing okay. So I'm going to go through design choices for the fluoroquinolone study and then walk through each of the modules. So here, our target was fluoroquinolone systemic exposure. We had 2 different comparators, different alternative antibiotics. We had an indication, which was urinary tract infection. And as Jack showcased, we actually had 3 different outcomes. We looked at aortic aneurysm alone, aortic dissection, and the composite of combining those things together. We examined 4 time at risk windows. We specified a restriction that everybody had to be over 35. We sampled a collection of negative controls, and the comparator selection tool told us what things to remove. Now, what I want you to see here is that we now have 1 target times 2 comparators. We only had 1 indication, but times 3 outcomes, so that's 6, times 4 time at risks, that's 24. So that means for each database, we were specifying 24 different analyses, different combinations. And that's relevant because oftentimes what I observe in the community and reading literature is that sometimes people will pick and choose how they perform sensitivity analyses, and they're not consistently thinking about the entire design space that you're operating under. Here, with no cherry picking, we said this is the full space that we're going to look at. Then yesterday, Jack cherry picked and only showed you one of those results, but that was only for brevity of time. As you'll see later this afternoon, when you go to the Shiny app, you will see all 24 of these results. Every result accessible and available for you to explore across every database that ran that study. Okay, so I'm going to go into some of the characterization modules. I'm going to highlight here that I told you that you want to pass in a target cohort and an outcome cohort. And the interesting thing is really what we're most interested in is the intersection between those 2 things. And so we can formalize that as there's a couple other cohorts that will naturally fall out. If you tell me a target and an outcome, there's some other cohorts that I could describe. There are the people who are in the target who did not have the outcome. So you can think about those as the lucky ones. Those are the fluoroquinolone users that didn't have the aortic aneurysms. And that's kind of that group in blue. And then there's the people who are the target group that had the outcome. So those are the fluoroquinolone exposed who had the aortic aneurysm. And we can think of those themselves as their own cohorts, and we may very well want to systematically study those. It's quite common in a lot of studies, for example, those exposed cases, which we can think of as that interaction group of target with outcome. We really want to know who are those people and what makes them special and different. And so in our particular case, when we specified fluoroquinolones and aortic aneurysms, what came out along for the journey in our characterization was that we also had the ability to dig deep into those people who had fluoroquinolones and got an aortic aneurysm. And that's just something that is a standardized output as part of our characterization. So one of the modules is cohort diagnostics. The basic idea here is anytime you're defining a cohort, you want to evaluate the cohort to understand its operating characteristics and its measurement error. By default, the cohort diagnostics package produces a wide range of summary statistics that are intended just to give you a sense of, did you really find all the people who had fluoroquinolone or did you miss some? Are some of the people who had urinary tract infection, are we really sure that they've got urinary tract infection? In the case of aortic aneurysm, I think Jack mentioned the work of Evan Minty in the community. We spent a lot of time looking at cohort diagnostics to really have confidence that we were finding all the aortic aneurysms and to dig in deep into the question of what is the trade-off between sensitivity, finding all the cases that were there, versus specificity and having false positives throughout our set. So the cohort diagnostics package is maintained by Jamie Gilbert, but it's another one of these modules that can run through this process. And so in this particular case, we passed to cohort diagnostics, target, the comparators of the other antibiotics, the indication, and all of those outcomes. And that means that each of these cohorts independently can be summarized and explored through the cohort diagnostics package. When we talk about characterizing features, we're taking advantage of 2 tools within the OHDSI HADES stack. we're using the tool called characterization that's maintained by Jenna Reps and a tool called feature extraction that's maintained by Anthony Senna. And the basic idea here is that when we take the target, fluoroquinolone, and the comparator and the indications, we're able to summarize those cohorts by themselves as well as that intersecting cohort of fluoroquinolones and aortic aneurysm. By default, what this package gives you is it summarizes demographics such as sex and age and race and index time. It gives you prior drugs, conditions, procedures, measurements, basically each of the clinical domains in the OMOP-CDM, and also computes some basic risk scores like the Charlson Index and the Chad-VAS score. So when we specified this module for our fluoroquinolone study, this meant we passed in 4 different target cohorts. We had our fluoroquinolone cohort, our 2 different alternative antibiotics, but also we passed in the indication as its own target cohort. So we passed in just people with urinary tract infection as a cohort because we wanted to just understand those people by themselves, independent of whether or not they got exposure. We passed in all 3 of our different outcomes. We passed in all 4 of our different time at risk windows, and that meant we were slicing and dicing our exposures and our indication and our outcomes in a myriad of ways. All of this information is now available. Incidence rates, we have a standardized incidence packet, or package called Cohort Incidence, managed by Chris Knoll. The basic idea is that you pass in a target cohort and a set of outcomes, and it is going to compute an appropriate incidence proportion and incidence rate for whatever time at risk window that you specify. In our particular study here, we chose to characterize the incidence, both of the target cohort fluoroquinolone, the 2 comparators, antibiotics, as well as the urinary tract infection cohort. So this meant we were going to compute incidence of how often does aortic aneurysm happen in fluoroquinolones, but also just how often does it happen in urinary tract infection in general. And that can provide us a specification there. We looked at all 3 different outcomes. We looked at all 4 different time at risk windows. And as a default, the incidence rate package stratifies the results by sex, age, and calendar time. So that can give you a sense of the degree to which there's heterogeneity in the experience of the patient population, or whether the incidence rates are actually stable over time. Some of our previous work in OHDSI suggests that whenever you are computing incidence rates, you should always stratify on age, sex, and time. Even though it's very common that someone wants to look in the literature and just get one incidence rate, we observe that if you don't do this appropriate stratification, that you really can miss out on some pretty profound heterogeneous effects. Characterizing time to event. This is also part of the characterization package managed by Jenna. Here, there are no settings that you have to specify. It is purely a descriptive summary that provides you, given a target cohort and an outcome cohort, give me that time to event distribution between those 2 groups. So in this particular case, we used our target, our 2 comparators, and our indication as our target input to this specification, and we passed in all 3 of our different outcomes so that we could look at that time to event relationship. To conduct the D-challenge, re-challenge analysis, there are a couple different parameters. One needs to actually specify whether or not, when you're doing a D-challenge, and I told you, you take the drug, you get a rash, you have to stop the drug, and you have to look to see that the outcome goes away. Well, there's time in between those intervals, and so there are parameters in this to allow you to say, when you do a D-challenge, how long you're going to wait before you can see an event again. And so these are some default parameters that we used. In the context of our fluoroquinolone study, we were able to do re-challenge, D-challenge for each of the exposures, the target and the comparator, as well as for the outcome. Now, importantly here, this is actually kind of interesting because a given person can be exposed to fluoroquinolones multiple times throughout their life, and the way that we've modeled our aortic aneurysm, it's possible that a person could have multiple aneurysms, although they must occur at least a year gap between them. But our time to event relation, our D-challenge, re-challenge can kind of give a sense of, for those people who had multiple exposure to fluoroquinolone, did we actually also see multiple aortic aneurysms, as an example here. Patient-level prediction. So this is relying heavily on two primary packages in the OHDSI community, the patient-level prediction package that GeneReps maintains and the Cyclops package that Mark maintains, which is really the workhorse to allow us to do large-scale regression. The basic idea here is that given a target cohort, we want to predict which of those patients go on to have some sort of outcome within some time at risk. To specify that, one needs to define the target population of interest. We usually use this as an incident cohort, whereby people are guaranteed to have some prior observation that we can use to identify predictors in that model. And then for those individuals, we look forward to look at some given time at risk window. As a default, we usually use fixed windows, so you can either think about, can I predict the thing that's going to immediately happen, or can I predict the thing that's going to happen in the future? Our default model is to do lasso regression using the Cyclops package, and there's some associated standard approaches to do machine learning that we have a default for. One of the things that is actually required for doing patient-level prediction is you have to have a sufficient number of outcomes in the time at risk to actually be able to faithfully train a model. We've seen lots of folks that are interested in this question of predicting, in this case, drug side effects, but many times we're dealing with rare drug side effects. And so if you don't have enough events that happens, that's really good for patients and really bad for data scientists who want to train machine learning algorithms because you just don't have enough data to do it. And so as just a general default, we actually need to be able to have sufficient data to be able to train these models. In this context, as you look through the Shiny app, you'll be able to see for our patient-level prediction, we train models whereby the target cohort of fluoroquinolone was used for all three of our different outcomes with all four of our different time at risk windows. So again, meaning in this context, 3 targets times 3 outcomes is 9, times 4 time at risks means that we're training 36 machine learning algorithms against each of our databases to see whether or not we can predict any of these outcomes. All right, so now I'm going to get into causal effect estimation. The primary results that Jack showcased yesterday was the results of our comparative cohort design. The idea that you have a target cohort and a comparator cohort. You are going to use propensity score adjustment as a way to make those groups seem sufficiently similar. And on the basis of that, we can then run some sort of outcome model. As a default, we take our target and comparator group, we restrict them to our indication. We ensure that we have some sort of new user design, and we apply a consistent set of restrictions to those. As a default, we are using large-scale propensity scores, which we've done quite a lot of research in the OHDSI community to prove is really robust to confounding adjustment. We use one-to-one propensity score matching, so that's why we saw in Jack's study, we kept getting the same number of people in the target and the comparators, because that was by design. We use a Cox proportional hazard model to produce our outcome rate, and then we calibrate based on our negative control estimates. So this is based on using the OHDSI package called cohort method that Martijn maintains, with the workhorse underneath of that being Cyclops that Mark maintains. So this standardized module, the way we ran it for the fluoroquinolone study, was we passed in a set of target comparator combinations. So we said fluoroquinolone and trimethoprim as one analysis, and then fluoroquinolones versus cephalosporins as a second one. So that's 2 target comparator combinations. We had our same 3 outcomes, our same 4 time at risks, and we used the default analysis settings. So what this meant was 2 times 3, 6 times 4, 24 estimation studies. Part of the reason I'm harping on these numbers and the combinatorics of things is that if you're going to read any one paper in the literature, you're basically looking at one of these. But here, because we have this standardized framework, we're able to consistently apply all of these. And if it's feeling a little bit monotonous, and it's not just because it's after lunch and I'm boring, but it's also because a lot of these parameters are the same parameters we're using for each and every one of these modules, that's not a mistake, that's a design feature. Because we don't want to be in the situation of cherry picking different targets and different comparators and different outcomes and different time at risks. We want to have a consistent, unified approach to answering the question. Our self-controlled case series design. This is a package that Martijn maintains called self-controlled case series. Underlying that is, again, Cyclops that Mark maintains. The idea here is that you provided a target cohort, an outcome cohort, and a time at risk. As a default, there's a series of design considerations for using an SCCS design that we kind of bake in. Importantly, what we do is we use the time that you're exposed in your target cohort, compare it to your unexposed time. We remove the time immediately before the target exposure because that can oftentimes critically bias studies. We actually have a spline in the model that actually adjusts for seasonal changes, which mattered a lot during the COVID times. And as within an SCCS design, one can use multiple outcomes. One can consider modeling to look for different outcomes, but one can also choose to just focus on a first outcome, which as a default is how we've done this. One of the things we hear, I know there's several epidemiologists in the room, and so I'm going to probably say something that's going to cause some outrage to some. Many traditional epi textbooks give you some sort of dogmatic statement about when you can use a self-controlled K-series design, and it's something to the effect of it must be an exposure that's intermittent and an outcome that's frequently recurrent. Otherwise, this design's not appropriate. There is nothing in the mathematics of an SCCS that actually dictates that that's true. And in fact, we've shown over and over again with lots of empirical studies, it's totally fine to run an SCCS across a wide array of situations, including some that you might have thought, hey, that doesn't follow the traditional dogma of an SCCS. The most important part is just, do you pass your diagnostics? And as Martine's going to go through, we have a wide set of objective diagnostics that helps to clarify this. And so if you pass the diagnostics, we feel good about the estimate. If you fail the diagnostics, you should not use it. And that does not necessarily correspond to the traditional epidemiologic dogma that you'll read in a typical textbook. So we ran an SCCS design for fluoroquinolones, and we also ran it for our two comparators, for our UTI, for all of our outcomes. Our analysis settings basically use the default. Turns out we failed diagnostics on all SCCS analysis for this study. So part of the reason that Jack didn't show it was because it's tremendously uninteresting. We didn't unblind anything for our SCCS design. I have to admit that I was a little bit surprised by that. Going into it, I wasn't sure whether or not we would pass diagnostics, but consistently across whatever it was, 13 databases, everybody ran this analysis, nobody passed diagnostics. And so I don't think in Martine's presentation we'll actually go through the diagnostics very much because there's literally nothing to see other than every database, every analysis failed the diagnostics in this particular case. Post hoc rationalization helps us understand that there was some time instability that was going on in a lot of these analyses. And if anybody's interested in this topic, happy to catch up with you in the next break or after we're done. But I want to just highlight that. All right, so, and I'm doing okay on time. So just want to come back to this big picture, and then I'm going to stop and open up for questions and challenges. The reason why I'm harping on this idea of standardized analysis design is because the hardest part about doing a good study is asking the right question. A lot of people have come to the OHDSI community and they've been overwhelmed by all the technology. Maybe they're not familiar or comfortable in programming in R. They see that we've got these like web tools. They don't know how to install a website, or they're just trying to figure things out. But all of that stuff is second order to the most important part, which is ask the right question. And we've actually put a huge amount of time in to try to help people ask the right question by formulating standardized, templatized questions that you can write words in, and translating those words into code that does exactly what that question asks for. What we're also trying to do is remove all of the degrees of freedom that a traditional investigator does when they play around in the data, investigate it, explore. What we're trying to do is say if we really want to trust evidence, we have to remove the threat of investigator bias. We have to remove the threat of p-hacking. We have to remove the threat of publication bias, and instead have a system where we pre-specify exactly what we're going to do, pre-specify exactly when we're going to actually look at the results, and be honest in only looking at the results at the end of the process. That's what we're aiming towards engineering, and I would actually say, like, we've now done this. We now have a package in OHDSI called Strategist, and this is exactly what we did for the fluoroquinolone study. Jack and Jung Ho and Nicole and Chan spent a lot of time making sure we were asking the right question, and we deliberated on that for quite a while, and we wrote a protocol. Once we wrote that protocol, up top, way up here at the top, we didn't deviate from those design decisions. Instead, we moved right into data diagnostics to figure out which databases we could run. We moved into phenotype development, and we figured out how or if we could appropriately phenotype aortic aneurysm. And then we went into our study diagnostics and produced the results. And this process, while we're showcasing the fluoroquinolone study, is the exact same process we went through on the other hemisphere for an anti-VEGF kidney failure study. And I would assert it's the exact process that you all should go through with whatever question you're dreaming up if you're filling in the templated Mad Libs questions. Because I think this is the only way we're going to actually get to the point where we have an honest, credible basis for generating evidence. And in the absence of that, we're going to continue to have research that other people will not trust because it's too easy to game the system and generate whatever answer you want by playing around in data. So come up with the right question and then specify the inputs in a very consistent, standardized way. If you can do that, there is a learning curve to figure out how to run the strategist package and run the analysis module, and we're going to go through that. But that's a second order issue. You can solve the problem of running a package as long as you can come up with the right question and specify the right inputs. So with that, I'm going to stop. I'm happy to take any questions, challenges, arguments that you all may have. Oh. Yes. And I have to say, you both jumped up, and I thought you were ready to ask a compelling question and not just hand out the mics. So I was really ready for a challenge there.
Thank you. It was really, really interesting and a great approach. I agree with the whole basic idea. And this is going to sound like a mean question, but it's not. It's just to generate discussion. So you put up this sort of slide with, you just have to answer these sort of 10 things, and that will prevent p-hacking. And I think actually, when I looked at it, I said, I think p-hacking occurs, or at least the design decisions that make differences occur in each of those sort of 10 steps as part of what you're saying. What's your cohort? That's where the decisions are kind of made. Yep. What is, I guess, the tension between having such a specified, you just put it into this package, and I guess for almost like the SPSS problem where you just kind of get a point and click, and you can just say, let's run it, versus almost the artistry of being a statistician, having to think about it, being iterative when you're saying we made this decision 6 months ago but it doesn't make sense anymore. Are you locked in, and is that a problem, or how much do I need to consider it in this framework?
That's a great question, Adrian. Thanks. So first, let me clarify the p-hacking thing, because I think it's actually important. The danger of p-hacking is that someone performs an analysis, looks at the answer, decides that P was 0.055 and they really wanted to be 0.049 because that's the difference between publication and not publication. And therefore, on the basis of what they observed, diddles with the inputs to get a different result. And so that is that iterative process of run the whole thing, see something, go back until you can play. And what we are actually trying very hard to say is, and actually I appreciated that you brought up, so I want to bring up that slide. So I am not at all, let me bring this one up. There we go. I am not at all, or I fully agree with you that this is where there's chance for investigator opinion to impact things. But importantly, if you do this up front, before you run an analysis, before you look at an effect estimate, before you look at your p-value, you remove the p-hacking, so long as you stay honest with, you specify this once, you generate your results, and you live with the results that come out. The SPSS analogy is actually a good one. The strategist framework we have, you got to do a lot of upfront work, and then this volume of stuff comes out at the end. It is not designed to be a highly iterative process. It's not designed for you to just, well, I got an answer, let's click another button and rerun the whole thing. It's a giant apparatus on purpose. And the purpose is you should put a huge amount of thought and consideration into this once, and you do need to live with it. Now, one of the things that you said I think is actually really important, that this artistry of the statistician. It is often the case, and I've experienced this many times over in my career, that you learn by exploring the data, you learn by understanding what's going on, and then that informs your decision. And you mentioned maybe months later and you're looking back at things. When we're doing retrospective analysis, the data is already sitting there. We can compute this kind of stuff in a matter of minutes or hours. This isn't a month-long process. In fact, as Jack can attest in the fluoroquinolone study, literally we did every week for 8 weeks. 1 week was execute. And it was a tutorial that told sites, how do you install and execute the code? And every site had to send back the results by the end of the week. So this isn't months or years that are going by. So hopefully you're not revisiting decisions over that short interval of time. Now, what can happen is, now that I see the results, I feel like I want to revisit decisions. And that's, of course, the real tension there and that's where you got to really hold yourself honest about, are you inducing investigator bias? Are you potentially playing a game of p-hacking? What I personally, this is purely my own personal opinion, not an OHDSI convention, but like what I think is actually really valuable is to think about, don't just ask the one question and then iterate. Ask the full set of questions that you might want to do, but pre-specify them all and make them all available. So don't do something like fluoroquinolone versus cephalosporin, and then after the fact to say, oh, you know what? Since I didn't get the results I like, maybe cephalosporin was a bad comparator. Maybe I should have picked trimethoprim. Instead, before we looked at it, we said, here are the 2 comparators we're going to use. And I think that it's really, really important, and part of our process that we feel strongly about, I think collectively as a community we feel strongly about, is if we're going to get to trust for ourselves and for the external community, we have to build in these safeguards. Randomized clinical trials are trusted, and a lot of people put the trust because of the word randomization. It's not about randomization at all. It's actually because you get one shot on goal to do this very expensive thing where prospectively the data was collected, the analysis was pre-specified, and you only get to run it once at the end. It's not actually the magic of randomization. It's actually the fact that you aren't in an easy, convenient situation to be able to game the system. Whereas when the data's sitting on my laptop, if I had SPSS, I can just run until I get P.049 and then publish. And so I think what we're trying to do is figure out alternative ways to bring the same rigor of a prospective study into the world of retrospective analysis. That's the best part of the video, actually, is just to be the back of your head for those few minutes.
So, Patrick, just on that, do you think then, unplanned subgroup analyses of RCTs is kind of what you're talking about there as well?
Oh, yeah, that's a really, really good point, Nicole. Yeah, so I said, like, it's harder to game a clinical trial. But actually, what is the game that people play is once the clinical trial data is collected, then they do exploratory analyses. At the point a randomized clinical trial has collected all its data and the data set's sitting there, it's a retrospective analysis. And that's why there's a big difference between the pre-specified plan and the exploration. And that's also why, like, regulators don't trust anything that wasn't pre-specified for exactly the same problem that we're trying to tackle here. Now, because you mentioned subgroup analysis, Nicole, I'll say, what is a valid thing to do is, given we perform this analysis and we gain some insight, it may raise a new question that we want to ask. Like in Jack's case, we didn't observe an effect. Maybe the question is there an effect within people over 70? Because we only did 35 and over. That's now actually asking a different hypothesis, a different question. That's not iterating on the same question, that's actually exploring a new space. And that can be fair game, though I would strongly encourage all of you to think about, like, pre-specify and think through all the questions you want to answer in one foul swoop to just try to mitigate how much error that you might be introducing in your design. Yep, here comes a mic for you.
Sorry, so on that point around if you're, then stratifying by age group,
Yep.
So when you're defining your cohorts, I guess, you would have lots of different cohorts. So all your cohort then different. So it's just a matter of defining them up front.
That's right. Yeah. So in this framework, you could think of, well, if I wanted a target cohort that was stratified 2 ways, I could just have 2 target cohorts, strata 1 and strata 2. Technically, in the bowels of the code, there's actually the ability to have subgroup cohorts. And so the idea is you could also specify a set of subgroup cohorts, and then we basically permute through every subgroup cohort for every target. But mechanically, all of that's doing is just creating a longer set of targets. And that's totally fair game. I would just encourage you to do it up front, not after the fact. I will say there's a difference between stratification, which is take your target and partition it into two groups, versus subgroup analysis, which is you could have multiple subgroups and they may be non-mutually exclusive subgroups. So very oftentimes we may care about a subgroup amongst people with renal failure or amongst people with hepatic failure, and there's going to be some subset of people that have both renal failure and hepatic failure. But that could all be specified in this framework.
Thank you. That's yeah, it's a wonderful process, and I like the idea of it. My question, I had two questions. One is, if you expect that maybe a study diagnostic isn't going to, say for the Cox proportional hazard model, you think it's going to, maybe there's some time varying that, like if that fails that, then you don't want to repeat the whole process, but can you change the method into, say, non-proportional? Like you have if it fails this, I can do this method instead.
Yeah.
Is that an option or?
That's a great question. Martijn, are you going to go through the slide that talks about protocol specifying versus diagnostics in the results? Okay. So I'm going to table it mainly because Martijn's going to talk about it. But briefly, you could think about it as diagnostics are your chance to determine what is feasible. And that is a reasonable thing that says if something fails diagnostics, you could make a change to try to pass diagnostics. Okay. The most important thing is our current stance is diagnostics are a blinding criteria. Yeah. So if you fail a diagnostic, you don't get to see the result. You only get to see the result if you pass a diagnostic. So that'd be like a fair and honest thing is like you fail a diagnostic, you look at it and say, I wonder if I could pass the diagnostics if I made a change. You're still free of investigator bias because you haven't seen the effect estimate. Okay. Where people get themselves in trouble, where I observe it and see it in literature, is you run a Cox proportional hazards model and you're like, well, I got the answer that I wanted, so maybe it's not so bad that I fail the proportionality assumption. Yeah. Or vice versa, I don't get the result I like, so now I'm more stringent in thinking about whether or not I failed the diagnostic. We don't want to influence ourselves by looking at the result. We want to keep that to the very end.
And the other question, which might come up later as well, is there a process for the missing data? Like, is that built in? Is that an analysis section that we I wasn't sure if missing data.
So I guess just generically on this thing. So I would frame missing data as, I'll answer your question, but reframe it. If we think about the phenotype development evaluation process, we are trying to quantify measurement error for our cohorts. Measurement error basically in your exposure is going to be exposure misclassification. It's either because people were exposed but you didn't know it, or people were exposed or people were classified as exposed but they didn't have it. A missing data problem, very pertinent and relevant, is like COVID vaccines, when data wasn't actually being appropriately captured. We had a lot of people who looked like they were unexposed because it was a missing data problem. I would frame that as a measurement error problem, that a phenotype had poor sensitivity. Same thing on the outcome side. Missing data as it relates to the outcome is going to be about whether or not you actually believe that the cases you see are right and some level of confidence that you have all the cases you're expecting to see. As it relates to features, which is where a lot of people think about missing data, the large-scale propensity score model that we're going to do, we use whatever's observed. It's okay if those proxies for features have missing data, because we're basically just trying to determine, is everything we observed adequately adjusting? So we don't need the features to be perfect. They don't need to have it's okay if they were to have some missingness. What we actually only care about is, do we achieve balance in the cohorts? And that's what the diagnostic is going to explicitly allow us to look at.
Thank you.
And last one.
More than a question, sort of a comment, just building on the question about missingness. So we do think about missingness as, an anomaly and that we want to handle, but sometimes missingness can also be an indicator of something. So in like diagnostic analysis, predictive modeling for health data, we need to be really careful, when we are handling missingness,
Yeah, that's a good point. I'll also highlight as it relates to that. So we have this this first step, data diagnostics. So you'll remember when you created the phenotypes for aortic aneurysm, we required that the aneurysm happen inside of a hospitalization. So turns out there's a bunch of data sets that we tried to run that had 0 events. Why did they have 0 events? Not because nobody in the population had an aortic aneurysm, but because the data sets were GP data sets. There were no hospitalizations in the data, therefore there were no people satisfying the outcome criteria. So they actually failed the first step, and those data sets fell out of the analysis. And so that's an example where we use data diagnostics to say, like, are you missing the most important thing? Do you not have the exposure? Do you not have the outcome? If so, don't even move forward. If you move forward, then we do this measurement error assessment to decide, like, do you seem like you have enough of the data? And then that carries on all the way through.